Hello and welcome back. This is video lecture 11.5, our final video lecture for chapter 11, in which we are going to talk about the content in chapter 11, section 8. Okay, chapter 11, section 8, which is going to be about conservation of angular momentum, our third conservation law. Before we get to that, though, let me remind you of one of the key ideas from the previous video lecture. Newton's second law for a rotating body, non-particle, extended body. Okay? It goes like this, right here. If you have a net external torque on your non-particle body, that will result in a change in that body's total angular momentum. And the net external torque on the body will be equal to the rate of change of the total angular momentum. So, right here, in words, a net external torque is required to change a body's angular momentum, and the net external torque equals the rate of change of the angular momentum. Tau net external equals d capital L dt. You need an external torque to change a body's angular momentum. External torque, that's a torque from an external force. Torques from internal forces are called internal torques. And apparently, according to Newton, that's what this is, Newton's second law, internal torques cannot change a body's angular momentum. Well, that's not shocking because internal forces can't change a body's linear momentum. Only external forces can. So this is the rotational version of that same idea. You must have an external torque to change a body's angular momentum. So as an example, we bring back the wheel. Remember the wheel that I can hold and I've shown you before? I hold about this central axis and I spin it like so. And there's not a lot of friction in the bearings, so it would rotate quite a long while before friction in the bearings would bring it to stop. So here's a body. This happens to be a rigid body. It's not changing shape, but it's an extended body. You can't treat it as a single particle, and it's rotating about an axis of rotation through the middle. And we learned in the previous lecture in principle, how to calculate that total angular momentum of such a body rotating about an axis. The formula was, just to remind you, I'll write it over here to the side, L equals I times omega, rotational inertia times angular velocity. So that's what we would use here. We would take the rotational inertia of this thing and multiply it by the angular velocity that it has rotating about this axis. Okay. Newton tells me that if I give this object a certain angular momentum, I times omega, the only way I can change that angular momentum is by applying an external torque. And the way I can do that is put my hand out here against the edge. Okay? That provides a force along the edge. There's a moment arm between that force and the axis of rotation, so there's a torque from my hand. My hand is acting like a brake. Okay? And because I have a torque, an external torque from my hand, I'm going to change the angular momentum of this thing. And that's the only way to change the angular momentum of a body. Apply an external torque. Okay, now let's extend that idea, or let's talk about an important consequence of that idea. And that's where chapter 11, section 8 comes in, and our third conservation law in this class, conservation of angular momentum. Okay, so Newton's second law for a rotating body has a very important consequence, and it is this. If you have a situation where the net external torque on a system, equals 0, then what happens? Well, you go up here to the new version of Newton's second law, and you put on the left side 0. Net external torque equals 0. Newton says if the net external torque is 0, then dL dt equals 0. dl dt equals 0. But we know that if a time derivative of a quantity is 0, then the quantity itself does not depend on time. It's constant. So, back to this consequence. If the net external torque on a system equals 0, then the angular momentum of that system is conserved. Okay, third conservation law. Let's recap the 3 conservation laws, and I recommend you write down what I'm about to say and put it on like a note card and have that note card in front of you all the time you're doing homework problems, because these are 3 of the most important ideas in this course, the 3 conservation laws. Number 1, conservation of mechanical energy. When is it valid? When the system you have chosen has no external work, no external forces doing work, and the internal forces doing work are all conservative forces. That's the condition for the conservation of mechanical energy. Second conservation law, conservation of linear momentum. What was the condition that had to be true? The net external force on the system you've chosen must equal 0. Then, capital P, linear momentum of the system, equals a constant. And now the third conservation law, conservation of angular momentum. When is that true? When, for the system you have chosen, the net external torque equals 0. Okay? 3 conservation laws, 3 separate conditions in which they apply. Let me give you now some examples, though, where, in the real world, you can see conservation of angular momentum in action. An example taken from your book, taken with a series of drawings here, is a diver diving from a board or a platform into a pool. And you've seen many things like this, and you've seen really impressive dives, but here's the basic idea. The diver pushes off the platform. In so doing, gives herself a slight angular velocity. Let's call it omega initial. Okay, a certain small initial angular velocity, I'll denote omega initial, which the picture shows is clockwise. So if I curl the fingers of my right hand clockwise, my thumb points into the screen. That's why you see the L vector there with an X. That means it's an arrow into the screen. So the initial angular momentum is into the screen. And it would be calculated using this formula. L initial equals I initial times omega initial. Initial rotational inertia. Okay, so we have a certain initial angular momentum, which is equal to the initial rotational inertia times the initial angular velocity. What's the axis, by the way? Well, once the person's in the air, the rotation occurs about an axis you see there that is through the center of mass, right here. Okay, we're having a tough time today. Okay, you may have noticed I'm having some technical problems. The Wi-Fi keeps going out on me, and so I'm pausing and resetting and so forth. Hopefully, we'll be okay at this point. So we have the diver with a certain angular momentum with a rotation about an axis through her center of mass, rotating clockwise when this initial configuration right here. Note the body is pretty much extended. Arms and legs extended far out. So pretty large rotational inertia and a very small angular velocity, not a huge amount of rotation in this initial picture. But then at various points during the parabolic trajectory of the center of mass, the diver can, of course, since she's not a rigid body, change her shape, adjust her shape. So what she does is go into a tuck where she brings her arms and her legs closer to the center of her body, such as you visualize right about there. In so doing, she has considerably reduced her rotational inertia, I. Why? because rotational inertia depends on how much mass and how it's distributed relative to the axis of rotation. The farther the mass is from the axis of rotation, the larger the rotational inertia. So in bringing her arms and legs closer to the center of her body, the diver is making her rotational inertia smaller. Okay, fine. So what is the consequence of that? Well, it turns out that the diver's angular momentum about the axis through the center of mass cannot change. It must be conserved. Why? Because there's only one force acting on the diver during the dive, F grav. Where does that force act? At the center of mass. Therefore, how much torque do you get about the center of mass? None, because there's no moment arm. So yes, there's a gravitational force, of course, on the diver, but for an axis through the center of mass, no gravitational torque. No torque, no dl dt. No dl dt, L is constant. Okay, so if the angular momentum of the diver is constant, now what have we done? We'll call this L final. That's got to be I final times omega final. We have made the I final a lot less than the I initial. But the L final must equal the L initial because the angular momentum must be conserved. So if the I got smaller in the final case, then the omega had to get larger. So in this final picture right here, there's a much larger angular velocity omega, in this case clockwise rotation. And that's what happens. As you watch the diver, you see more rapid spin, rotation about an axis through the center of mass. Then the diver untucks just before hitting the water, making the rotational inertia large again, but angular momentum must still be conserved, so the angular velocity must get small again, so there's very little rotation just as she enters the water. It's an example of conservation of angular momentum in action. Let me show you two more examples. One that I always do in the classroom when I am in my main classroom and I have all my equipment. This one I'm going to show you on a video on Wiley Plus. Hopefully. All right, it's going to be a video here where there's going to be a professor sitting on a stool that rotates. Let me get it going here. Okay, so the professor is on a stool that can rotate and is holding a couple of small dumbbells. And it's going to start out with the dumbbells held out to the side and a small angular velocity. And then it's going to bring the dumbbells closer to the center of his body. What's going to happen to his angular velocity then? So he's talking to you, but I can talk to you. And he's just explaining what he's going to do. So he's going to give himself a somewhat small initial angular velocity about a vertical axis with the dumbbells held out. And then it's going to bring them in. Notice what happens to the angular velocity. And then take them back out again. And what happens to the angular velocity? Okay? All right. So there you saw another example of conservation of angular momentum at work. Let me draw some pictures for that over here to the side. Very simple representation of the person on the rotating stool. Okay? First, an initial picture. Draw like a physicist. There's the person on the stool. There are the two dumbbells held out to the side. There is an initial angular velocity, omega initial, about a vertical axis. We're going to assume there's negligible friction in the bearings of that stool. And if that's true, then there's negligible external torque. So the angular momentum must be conserved. So whatever initial angular momentum we have here, it'll be the product of the initial rotational inertia about that axis times the initial angular velocity. In the so-called final picture, the person on the stool has brought the dumbbells much closer to the center of the body, what has that done to the rotational inertia? Did you say that it makes it smaller compared to the initial rotational inertia? And if that's true, what happens to the final angular velocity? Omega final. Well, assuming conservation of angular momentum, L initial equals L final, then, just like with the diver, if you change the rotational inertia, say make it smaller, then the angular velocity has to compensate and get bigger, because the product of I and omega must stay fixed. And then when the professor brought the masses back out again, that increased the I again, and it makes the omega small. Can you think of another situation where you've seen that kind of thing at play? Did you say ice skating? What do ice skaters do? Well, they get themselves spinning with their arms out, and then they bring them in, and then they rotate very rapidly, and then they bring them out again. Conservation of angular momentum. Okay, now let me show you another application of that. A little more complicated, but visually rather striking. Okay, let me make sure I'm showing what I want. Okay, it's a video of yours truly, and I've got that bicycle wheel on the handle that I've shown you many times, and there's a turntable you see that I'm going to step onto. So let's see here. We don't need any audio from me. I'm getting it spinning very rapidly clockwise as I look at it from above. Then I stand on the turntable, making sure that I'm trying to be at rest initially, but, okay, hold it. Hold it, trees. I want it more like that. Okay. I'm at rest on the turntable, no rotation. But the wheel is rotating as I look at it rather rapidly clockwise. The system is me and the wheel and the platform. We're going to assume very little friction in the bearings of the platform, so no external torque, so angular momentum should be conserved. And then I'm going to turn that wheel upside down, which means it's going to change from rotating clockwise to counterclockwise. And that's going to change the direction of its angular velocity. And since L equals I omega, that's going to change the direction of its angular momentum. That means I've changed the angular momentum. But the overall angular momentum of the system cannot change. So I, meaning my body and the turntable, must rotate the original way clockwise to keep the total angular momentum the same as it was before. Here we go. So I turn it over, and now I rotate clockwise. And I turn it back, and then I don't rotate. And then I turn it over, and I rotate clockwise. And I turn it back, and I don't rotate. Okay? The system will rotate however it needs to rotate so that the angular momentum later has the same value that it had to begin with, if there is no net external torque on the system. Okay, all right. So we're going to be doing a Wiley Plus problem together in class on Monday. But before we finish today, let's do a little more practice with the concept of conservation of angular momentum. That's more indicative of the Wiley Plus type of, the thinking you're going to have to use to solve Wiley Plus type problems. Okay, so here's going to be some practice with conservation of angular momentum. The figure below shows an overhead view of a rectangular slab that can spin like a merry-go-round, or carousel, about its center at O. Yes, it's an odd-shaped merry-go-round, but don't worry about it. It can rotate. Let's say it's got a length this way, little b, and a width this way, little a. It's a rectangle. But notice it's rotating about an axis there in the middle, O. Also shown are 7 different paths along which a wad of bubblegum can be thrown, always with the same speed and mass. And it's going to then stick onto the initially stationary slab at the place where the arrows touch. Okay, so in the first case, we throw a little piece of gum with a certain mass and velocity in the direction of arrow 1, which means the wad of gum is going to collide and stick right there on the merry-go-round. And we're going to do these little experiments. There are 7 of them, one at a time. Always with a wad of gum with the same mass and speed. And the slab is initially stationary, as you see. But notice what we're going to have is a collision between a wad of gum and a merry-go-round. And we're going to take the system to be the things that collide, the wad of gum and the merry-go-round. But afterwards, we're going to have rotation of the merry-go-round. So we have a collision with rotation. As far as this chapter is concerned, if you have a system of colliding things that rotate, it's conservation of angular momentum you should apply. Notice when we had collisions with linear motion, chapter 9, we used conservation of linear momentum. Now we have collisions with rotation. We're going to use conservation of angular momentum. So we're going to have 7 collisions one by one, and we're going to enforce conservation of angular momentum about axis O. Okay? So the angular momentum of the system just before the collision must equal the angular momentum just after. The system is the bubble gum and the merry-go-round. Okay? So the idea we're going to use is L initial must equal L final. Okay? All right, now what are we supposed to do in this practice, at least in part A? We are to rank the 7 paths according to the angular speed, I'll denote that omega final absolute value, angular speed that the slab with the piece of gum on it has after the gum sticks greatest first, after the collision. Okay? In which scenario of the 7, with the gum thrown along the direction of the 7 different arrows, will the thing rotate fastest afterwards? Right? That's what it's basically asking. But the way we're going to answer it is we're going to enforce conservation of angular momentum because we have a collision with rotation. All right, now for the L final, let's use the formula. Okay, we'll have a piece of gum stuck onto a rectangle. Piece of gum stuck onto a rectangle. Don't worry about the contribution to the gum to the rectangle itself. It's small. So this L final is just going to be the rotational inertia of the rectangle times omega final. I'm really only going to do here magnitudes in part A. And in all 7 experiments, the I is the same because the shape of that merry-go-round is the same. Don't worry about the fact that the piece of gum is in a slightly different location in each of the 7 experiments. The gum is small compared to the merry-go-round. All right, so I'm interested in what the omega final absolute value is. So that's going to equal that. L initial absolute value over I. And since the I is the same in every one of these 7 different little experiments, the way I'm going to rank the omega final values is by ranking the L initials, the initial angular momentum, okay? So in which of the 7 experiments do I have the biggest initial angular momentum? That's going to be the case where I have the biggest final angular speed, the greatest rotational rate. So what I have to be able to do in these 7 experiments is basically rank their L initials, magnitudes, largest to smallest. So I'm going to do that. I'm going to go one by one, 1 through 7, and I'm going to write down something, whatever I can, about the L initial magnitude in each case. Okay? All right, let me start with experiment number 1. Let me draw my own picture. There's the merry-go-round. There's the axis of rotation. There's the bubble gum just before it collides. Okay? Let's draw its linear momentum, P. Okay? In this case. That's the direction it's going. Let me extend that. You could call that the line of action, if you like, for P. I need to be able to write down something about the magnitude of L initial. Now here, note the only motion is due to the bubble gum. The rectangle isn't even rotating yet. And you might be thinking that a particle moving in a straight line doesn't have any angular momentum. Oh, but it does. R cross P, where R points from O out to the particle. Now in this case, the handy way to think of, and I only need the magnitude of R cross P, the handy way to think about that is to take the magnitude of P times the moment arm, just like you would for torque. And the moment arm is the perpendicular distance from O to this line of action of P right there. Let me just call that distance little d. I can see that little d is less than A over 2. A is the width of the rectangle. So this is magnitude P times R perp. That's mvd, where m is the mass of the bubble gum, v is the initial speed of the bubble gum. Remember, that product is the same in all 7 experiments. Okay, that's at least something about the initial angular momentum. It's m times v, which is the same in every experiment, times that distance d that you can see, and it's very clear that d is smaller than half the width of the merry-go-round, A over 2. Now let's go see what we can say about the initial angular momentum in experiment 2. Let's go back up to the original picture. Look at arrow 2. That's the direction of P, of the bubble gum, just before the collision. They've already given me the line of action right there. Notice it passes through O. So what's the appropriate moment arm for the angular momentum? It's 0. So the initial angular momentum in this case is 0. So how much rotational speed am I going to have after the collision? Omega final. None. It won't rotate at all after the collision. Okay, well that's easy to rank. Now let's go on to experiment 3. Look at arrow 3. See it? Notice they've also drawn the line of action for us there. Notice it passes through O. So the moment arm is again 0. So the initial angular momentum about O is 0. So after the collision, the angular speed will be 0. No rotation. Again. All right, now let's go on to experiment 4. Okay, that one's going to be a little bit more complicated. Let me draw my own picture. There's the slab. There's point O. Now, the arrow 4 shows me that the bubble gum is going to hit right there on the corner. Whoops, I lost part of my rectangle. The bubble gum is going to hit right there on the corner, and just as it hits, its momentum vector is that way. So there's its line of action. And so its moment arm is the perpendicular distance from O to that line of action, which the picture tells me is right along the diagonal there. And that R perp, well, I'll just tell you. Remember, I already gave you the dimensions, A and B for the slab, is the square root of A over 2 squared plus B over 2 squared. I'm talking about this distance right here. Okay? So, L initial magnitude is M times V times that moment arm. Okay? And although I don't know actual numbers for A and B, I know that square root of A over 2 squared plus B over 2 squared, that purple distance there in picture 4, is larger than the distance D in my picture number 1. Yes? So I know the L in 4 is bigger than the L in 1. Now let's do 5. Okay, look at that. You may not be able to see it. I'll bring it back down. Look at 5. Look at arrow 5. That's the momentum. Okay, there's the bubble gum. Just as it strikes, the arrow 5 is the direction of the linear momentum. There's the line of action. It passes through O, so it has no moment arm. So it has no angular momentum. So R perp equals 0. So the magnitude of L initial equals 0. So the magnitude of omega final equals 0. No rotation. On to 6. I'll draw a picture down here. Okay? There's the merry-go-round. Point O. The bubble gum in case 6 is going to hit right there. And just before it hits, its linear momentum P is going that way. It's directed that way. So now I need the moment arm. Perpendicular distance from O to that line of action. That would go right like that. But that means that's half the width, or length if you like. B over 2 is what that would be. Yes? So L initial is mvb over 2. And then one more, 7. And I'll draw one more picture. There's O. The bubble gum is going to hit right there, and just as it does, its momentum vector is that way. So there's the line of action. Now comes the moment arm. Perpendicular distance from O to that line of action is right there. What is that in this case? It's half the width. A over 2. So L initial is mv A over 2. Now we just have to rank them. It all boils down to the moment arms. Okay? Much like an earlier class engagement exercise where we ranked torques on a square-shaped object by ranking moment arms. Okay, in any event, we have this angular momentum up here, mvd, right there. And then, of course, we've got several that are 0. Then we've got mv, that value, square root of a over 2 squared plus b over 2 squared, and that value, mvb over 2, and that value, mva over 2. And we just got to kind of be careful about which one's the biggest and so forth. I'll rank them by the number of the case 1 through 7, from starting with the biggest. Okay? We're ranking L initial, but that's also going to rank omega final. Yes? The biggest one is case 4. That has the biggest moment arm. The next biggest one is 6. That has the next biggest moment arm. Then 7. Then 1. Then, I'll put a semicolon, 2, 3, and 5 tie at 0. So that's the ranking of omega final, the final speed. Okay? Now, there was a lot going on there. So if you have any questions, you might want to ask during class on Monday. Okay? But let me leave you with a class engagement question for this practice. It is the part B. In this practice, part B, it says, for which of the paths of the 7 of them will the angular momentum of the slab and gum about O be a negative quantity? What that means is it's directed into the screen from the point of view of the figure. All right, I just want you to list of the 7 cases, which ones are going to result in an angular momentum directed into the screen. So I want you to answer that. As class engagement on Blackboard. Okay? And that is all we're going to do for this video. We'll do an example problem in class where we will do a Wiley Plus type situation where there is a collision with things rotating. But that's all for this video.